All right, so here, okay. So I guess last time I talked about in words what I'm trying to do here, but I guess today I'll just add in a few things, some pictures and some literature review. So yeah, thank you for giving me this opportunity. I'm Paul, and my topic is going to be about corotational, I guess, beams and shells. I'm going to base off the corotational shell with the beam finite elements. But what I'm very interested in doing is trying to analyze kind of like a parametric study if I have time, but between a castellated versus a regular I-beam. Uh, so to start off, I'll just talk about a little bit about some of the applications of corotational systems, and I guess a little bit about the theory and how it was analyzed and what we do now, and then I'll show you some of the modeling that I'm preliminary, and then my plan for the analyses. So briefly, I just got these from these information from these two sources, and so over the past few decades, what we're talking about here is geometric nonlinear finite elements of flexible beams or shells and frames, and they typically get analyzed with large deformations. And remarkably, it's still an open research subject, and new applications in industry still need to be treated. Some of these are flexible hoses in the offshore industry. What you see here is what I'm really going to focus on is mostly on civil structures, um, and they've been also been applied to flexible aircraft. Uh, Additionally, some applications are in large wind turbines, and there's others even so to analyze plant stems. So now to talk about the theory. So what you see here is a beam configuration, but it can also be extended to shells. The two main things are geometric nonlinear analysis. This is to analyze flexible structures and others. But how this was done um, is three different kinematic descriptions: total Lagrangian formulation, and updated Lagrangian formulation, and what will lead us to the corotational formulation. So just to define these just a bit, the total Lagrangian formulation is the oldest kinematic description, and it is most widely used in finite elements. This formulation is where you have the system of equations that are defined in fixed global coordinate system that doesn't change with the analysis. And large displacements and strains are found in this formulation, which needs the special handling. So altogether, because of this, the system of equations could become very complicated. So this leads us to the updated Lagrangian formulation. In this description, the system of equations are defined in terms of a coordinate system that is updated with the last accepted solution. And using the system, it's kept fixed, but the system equations are much simpler compared to the total Lagrangian. But even so, the displacements from the current configuration to the last is large. When it gets large, then the basic assumption is violated. So the results can be compromised. So that's why I'm trying to study this corotational formulation so that we can avoid this. So now the reason why I'm using steel is it's very, I guess, prevalent in modern construction. These can be found in a lot in like sometimes hospitals and then warehouses, especially and mostly in industrial buildings. And what's great about it is architects really find it to be aesthetically pleasing, and I guess these holes that you see can also offer some flexibility. And so its main advantage is the high loading capacity, and then it has reduced weight as well. But the one thing that the reason why I want to study it is because it can be prone to more so in buckling, and because it has holes and stress concentrations. And just to, I guess, to show the configuration for corotational. So these are just, this is the beam. And I talked about this last time, but so you have two coordinate systems. So you have the, I guess, the global frame, and then you have also the local coordinate system. And then so with this, you can decouple the rigid body motion from the deformation. And we've heard this before, but the one thing I haven't done is actually create like a finite element kinematics of how this is done. And then this is for a shell, which I'm going to be doing for this project. And what's seen here is triangular elements though, but I think I'm going to use quadrilaterals. So yeah, that's in the same case. Yeah, you have these two coordinate systems, and then you have the rigid body motion, and then the current undeformed, and then deformations. Yeah. So now I guess I'm gonna talk about what I've modeled. These are preliminary. I just want to show you guys. So the two models I have so far in Abacus, and then I did this in CAD first, and then I imported it. So the first model is a corotational regular I-beam. So this is no structure, but then I'm going to be using shells for the elements for these two. And then the next model is the Castellated I-beam. So yeah, you have these holes. So that's the only difference. How I chose these is so I made the weight per linear foot to be the same, just to be consistent, and then I just picked different depths. And then the span is just from a source where I got typical sizes for these cross sections. And then I also have, so this is the CAD that I use to model these. And then just to make them more, for both of the models, I'm gonna be using this type of material. And here is gonna be the load that I've chosen. This I might change, but this is what I have for now. And typically, a lot of, just to confirm like accuracy, I was thinking about doing just a cantilevered beam, but I wanted to explore like I guess the different configurations of boundary conditions, like the full span from full fixity to partial fixity. So this is the reason why I'm trying to explore these two things. And this is my last slide, but this is where I'm at right now, which I may need some help with creating the finite element, like coding. I guess two main things here is I'm going to be doing a mesh development and a convergence study. And so for the mesh development, I'll be doing so I'll be doing a P refinement and H refinement. So for the P refinement I'm choosing to do a linear first for shape functions, and then if I get that to work, then maybe quadrilateral and quadratic. And then for the H refinement, it's just I'm gonna see. I guess I'll compare the error with each element size. And my main goal here is to create this corotational shell element. Hopefully next time I'll be able to show that. And for the convergence study, I'm hoping to get through all four of these, but I'm going to start out with the static analysis, and then the dynamic, the buckling, and then the stress concentrations. So yeah, that's pretty much it.
All right, do we have questions for Paul? Hi, Paul. Are you going to consider material nonlinearity as well?
Yeah, I was thinking about it. I was thinking about that, but I need to get something to work first. I'll think about that. Yeah.
So also, are you going to compare that with like analytical solutions? Like you have a cantilever double fixed beam. Are you
Oh,
going to compare that with the simple equation provided by like hand calculations as well?
yeah, yeah. I'm actually gonna compare the finite yeah, numerical solutions with the analytical. Yeah.
Great, nice. So Paul, I think it would be helpful if you were to study one of the papers on the corotational finite element technology and then explain
Okay.
to the class the main points. You hinted at the corotational frame being crucial. So if you could explain how that actually works, I think that would be a good next step.
Okay.
So for your next presentation, which might be sometime next week, if you could study that up.
Okay. You said a paper. Do you know what paper?
I would probably suggest one. Um, I can probably type in here the name. You
Okay.
will find Carlos Felipe's paper on corotational formulation. I